I'm going to show you how to build a inverted delta antenna. And I'll share the files with you so that it'll fit on a 1/2-inch rod that you can drive into the ground. And of particular interest to me today is the Balun that I made for it. It's a 4-to-1 guanella. So if you're worried about how you stay in contact with your friends in an emergency or anything of that sort, you'll have something you can pack right into your backpack. Inverted delta or any loop antenna requires a balanced input. That's not such a good thing because most radios these days have coaxial, which is an unbalanced output. We need something to bridge the gap, and we need to understand how that works. Coming out of most radios is a round shield and a center conductor. And that center conductor is where the radio energy exits the radio. Typically, we'll add a piece of coax with another connector. The cable is a piece of metal on the inside, just a solid piece of copper, followed by some copper braid all around the outside, called the jacket. And the idea is that when this signal travels down this center conductor, any radio energy will actually live in the dielectric material surrounding the center conductor. The center conductor isn't where the energy is. The changing electromagnetic fields exist between that center conductor and the external shield. All of the polarization is happening in the area around the center conductor, between the center conductor and the shield. When you get to the end of the cable and you throw an antenna on there, the energy starts to escape and radiate outwards. But what happens if it reflects on something? Does the energy go back? And the answer is it does, but it doesn't go back inside the cable. It'll start traveling outside the cable. And we don't want that. So we'll add this thing called a choke. And a choke is a magnetically permeable material. Usually we use iron and nickel alloys and other such things. And the energy will hit this thing and it'll get absorbed into it, and it just turns it into heat and it goes away. Now let's take a look at an antenna. The antenna that we're building is an inverted delta antenna, and what we ideally want is that we drive each end of this antenna with an equal and opposite signal. If you're familiar with voltage versus time graphs, you know, like you might see on an oscilloscope, we'd have two equal in amplitude, 180 degrees out of phase signals feeding each of these antennas. But remember, I said our feed line, the energy is traveling around the center conductor till it comes out. So which one do you hook it up to? Well, you can't. You need this thing in the middle called a Balun, which connects the balanced output to the unbalanced input. How the heck do we accomplish that? Let's find out together. It's physics. Love physics. Surrounding every wire is a field, and that field can store energy and it can release energy. What's really happening is that we're polarizing parts of it, and we can use that to push electrons around atoms. So if you have a signal traveling down this wire in this direction, it's going to manipulate the field around that wire. If we then put a second wire around there, this changing electric field is going to push on electrons and create a second one back the other way. So the longer this signal travels down, the bigger this return can be. And it grows, so as this signal goes down, this return is going to get bigger and bigger and bigger. Put our signal down one wire and then have it come back on both. We can turn our unbalanced to a balanced output. It turns out that magnetic fields in air are pretty weak. Nothing is going to beat a magnetic field in a metal. So typically what we want to do is take two loops of wire, wrap them around an iron core, and when we run a signal through the first wire, it's going to create a changing electromagnetic field in this core, and then that core is going to create a changing electric field in this wire. So an unbalanced input will become a balanced output. Hopefully that kind of works for you. I put in a positive going signal here. I get a negative one out here. I put a negative one in here. I'm going to get a positive one out here. That's the way it works. So now I've got some cool animations surrounding all atoms or electrons, and the direction that those electrons spin is what gives us the field. And if they all spin in one direction, you get a strong field. If they're all out of order, you get no field. And, you know, if you've got a little more than the other, you get a field. It's just not as strong. So we tend to call that spin. They're spin up, they're spin down. But if you broke these atoms into a grid, you know, I'm going to start off with these things somewhat randomly assigned. The electrons are spinning all sorts of different ways, either spinning up or spinning down into the atom. Well, if you had an infinite grid of this stuff and you applied an external electric field, so right now we're kind of, you can get these things to change. You can get these things to flip. And the thing that impacts any given atom, in this case, the center square one here is the only one I'm looking at, is what's going on with the nearest neighbors, what's going on with the external field, and what's going on with just a little bit of randomness that always exists in nature. We typically refer to that as the temperature T. So if this guy is going to flip or if he's going to stay in the same direction, it depends on what's happening nearby, what's happening, the strength of the electric field, and what's happening, because there's always just a little bit of randomness that we call temperature. I've got some ridiculously cool animations I made to share with you. There's this thing called an icing model. So if you have something, be it magnetic domains or whatever, over time it goes from random to ordered. You start getting this corseting effect that's happening. You go from this highly disordered system to a more ordered one. And if you've ever looked closely at like grain boundaries in metals, or, you know, this happens in crystals, it happens in lots of different things. What I'm about to do is take this field and flip it. So we're going to see the field go one way and then the other, and then one way and then the other. A fast changing electric field. You know, we're going back and forth. We're never fully saturating anything. Here it is with a little bit of a graph. You can see with every little bit of energy that we put in, we're kind of in this constant change, and that's a good thing, because the constant change means we're putting energy in and we're getting energy back out. We're putting energy in and we're getting energy back out. We're not losing much. But let's watch what happens if we change the frequency too slowly. And let's see if this is the right one. So here we're changing it very slowly. And you'll notice that, you know, we're still putting energy in, and we're not seeing really anything change. We're not seeing flips. So the energy that we're putting in is wasting. It's going towards heating the core. I'll play that again. And the reason that this is important is for what we're about to do to work. We've got to be flipping these things to put energy into the core. We've got to flip it fast enough that we can still keep getting energy back out, because at some point you just saturate and you're putting more energy in and nothing's happening. So let me show you just of a simple quench magnetizing something, and you get all these domains. Spin up is, you know, white, spin down's black. Let me show you fast again. Okay, we're constantly changing, and we're constantly seeing change. Versus we do this thing too slow. We're still changing, but we're not seeing change. We've saturated. We don't want it. Saturation's bad. What we're going to do is create a Balun, and this was created by Guanella. Take the unbalanced side. I believe we cross these. All right. So my signal is going to come in over here. This is the unbalanced side. Ground's over here. It's going to come out over here balanced. So what I'm putting in here is just a sine wave, and what I'm going to get out here is a sine wave and another one with equal and opposite balance. Okay, the Balun itself is 3 prints. I threaded this, although it turns out that ended up being a huge waste of time because it leaked anyway when I went to pot it, but I tried. You could just not have the threads and it would be just fine. But the idea is that we wrap the coils and we set them in here. We put this in, wire everything up, close it, and we're done. We've got 2 of these. We have some wire. This happens to be 18, but I think 16 is recommended. But this is just enamel magnet wire that I have twisted together and wrapped the ends on. Woo! We've got some BNC connectors, although we just need 1 of them. I've got 2 here in case I screw something up. And then we've got some banana posts, but I'll just grab a couple more of those out of storage. So how long do these things need to be? That is a fantastic question that I'm afraid I don't have a terribly good answer for you on. There is a diminishing returns after you wrap these. The number of wraps doesn't really affect the impedance. The impedance is more affected by the wiring. These things appear to be about 28 inches long if you're making your own, and at some point you're going to have to strip the wire off the ends of these. The easiest way to do that is usually with sandpaper or something. They do make these really cool tools. They're about 40 bucks, and they just go on and they spin, spin, spin. Let me undo that a little bit. Woo! And that is about the easiest way to do it, in my opinion, but there's lots of different ways that you can do it. On the cores, we're going to have these things wrapped in opposite angles around them, and the way that I'm going to keep track of everything is I'm going to have the blue sides facing each other. One is going to go this way, and I'm going to hold these up to show you in just a second. One is going to go this way. So I'm just marking these so I can keep track of what's what, because I don't want to screw that up later. I'm going to start with the middle here, and I'm just going to feed this up so it's grabbed on the bottom of that. Then, as much as I can with this clamp that I'm trying to not crush the core with, but can be a little tighter. On this first one, I am going to wrap in this direction. So the one closest to me goes to the right. The one furthest from me inside the core is going to go to the left. And for me, I am just going to start here in the middle, drag them through. Don't like that knot that's showing up. And I want these things to be as close to the ferrite as I possibly can get them. And I have heard tale of people using hammers to make this happen. I've heard tale of people using pliers to make this happen. Okay, get rid of that knot. I twisted these things up by holding them both in a set of clamps at one end and twisted them about 20 times each. I'm sure there's an optimal number, but I do not know what that number is. And just to make things a little tighter, I'm going to grab these things and yank on them. Don't want these things to necessarily overlap, and we'll work on the spacing a little bit more in just a minute. I'm just going to use this for QRP, but if you are doing higher power, you can get some pretty high voltages in these, and the solution to that is to wrap these things in heat shrink or PTFE. There's winding number 1. Winding number 2 is going to happen the same way. I'm going to fold the wire in half, start on the blue side, and in this case the one closest to me is going to go to the left first, and the one behind me is going to go to the right. So in doing this, I'm getting the wires wrapped in a right-hand direction on one core and in a left-hand direction on the other. And again, you just kind of want it as tight as possible. This one's looking a little better than the previous. The easiest way to figure out how much wire you need is to wrap it with a string first. And then once you have the string, it'll tell you. Let's see how many more we can do here. All right, now we've got 2 cores. And now I'm going to put one on the other. I'm going to start doing some electrical connections. I used 2 different colors of enamel just because it'll be easier for you guys to see what nonsense that I'm involved in. The 3D print has, they're kind of hard to see, but there's these 3 reference markers, 1, 2, 3, that match up with 3 reference markers here, right here. 1, 2, 3. So you can, when this thing is threaded on, this is the side of the container that is going to be lined up with those 3 spots. I also put a 3D printed a spacer just to keep the coils from rubbing on each other long term. Let me go back to my diagram real quick. Guanella Balun, I've got red and orange wires feeding into each one and red and orange wires coming out of each one. What I'm going to want to do over on this side is connect the 2 oranges together, short them out. I'm going to give the 2 red, and those are going to get connected to the Balun side. We're going to make it this way. So I'm going to short the 2 oranges together, and then I'm going to have a red balance, but then I'm going to have orange red mixed, orange red mixed. So that's what we're doing, because I built that, I tested it on my scope, I know that works. I don't want to have any issues with the currents inside and outside the coil and all that stuff. So anyhow, I might have to do a little bit of cajoling, but these coils fit, not well, but they fit, and they go inside. All right, we'll start heating up the iron and go from there. So diagram, 2 oranges, that's what I'm looking for first. So I'm going to get those things isolated by untwisting them. And then I'm going to get them married together. And I'm going to get some pliers to hold them while I solder. And Andy says this will be fine for 50 watts. I'm going to trust him. Let you guys get up close and personal on cam 3. I'm always a big fan of flux. To deoxidize and lower the surface tension. And then, come on, Mr. Solder. There we go. Gonna heat that up. Solder goes where flux flows, so come on, big guy. Let's add a little heat here. Make sure we're melting. Make sure the tip's tinned. I don't know if you guys can see that at all, can you? It's very small amounts of solder so far. I only have a small one available to me. I am going to show you a trick that I sometimes do in cases like this when my depth perception gets the better of me. Whoops. I'm just going to wrap some solder around it. Let's do it this way. I've already fluxed it, so now I'm just going to heat this up. And we'll let it flow right in between. You can see that there is probably some enamel that wasn't cleared off there. That's keeping those things from sticking. So now those two center orange ones are stuck together. That's what we want. We can trim off the end and fold those over, and a little bit later we can cover them in heat shrink tubing to prevent any short circuits later on. All right, those two are done. Let's go back to the diagram and figure out what we're going to do next. So this is done. Next up, I need red and orange paired to the center point of the BNC connector. I'm going to need red and orange to the ground of the BNC connector. On the other end, I'm going to need red and red for the output of the device. That's going to go to the banana, and then I'm going to have red and orange and red and orange. So the first thing I'm doing is isolating and separating those, which I can give you a better view of. I didn't really quite have enough wire. I could have used a little bit more, but what's done is done. So what we're going to do is marry these two together and then marry these two together. And you'll see that there could be some short circuits, so I'm going to fix that with heat shrink tubing to prevent it. Oh, what have I done? I tell you, I'm the reason I can't have nice things. Okay, we're going to make this work. So I'm going to take a little bit off this guy and a little bit more off this guy. And then I'm going to find some heat shrink. Got a ton of it here. So all I'm trying to do now is get this heat shrink down over the exposed wire. So maybe about that long. Again, since I pre-stripped this stuff, I could potentially have caused myself a little bit of trouble. And I could have made these wires a little longer too, but I'm just pushing it down over these things just to make sure there are no unknown shorts. Right? I don't want to know every bit of trouble that I'm causing. And I might need to add a little bit of wire to these two, but again, not the hugest deal in the world. The enamel is still plenty long on these, so it's not really an issue there. I just have to mechanically connect them, and then I will electrically connect them. Solder is not a very good mechanical bond, so whenever you can, make mechanical bonds for strength. Don't worry, we're going to cover these two. Again, I always like to use a little bit of flux. Solder goes where flux flows. It lowers the surface tension, deoxidizes any metals. And you guys are probably yelling at the screen right now, like, why are you all over the place with that solder? And the truth is, I've got pretty horrible eyesight. Most of this stuff, if I wasn't on screen, I would be doing under a microscope. And it wasn't that way when I was younger, I'll tell you that much. But that's okay. All right, so there's one. We'll cover that. This one's going to be a little bit trickier in that they're both short. So I'm just going to pick one, and then we'll likely just add a short piece of metal just to make life easy. So I grabbed another piece of enamel wire. I'm going to make a lengthener, and all I'm doing right now is just drawing it through the tool. If I had gone for 19 inches instead of 18 and 18, I wouldn't have had this issue, but I was getting stingy with the wire, getting too clever. So now all I want to do is get these things bonded together. And then once we solder them, I'll put on some heat shrink and all our issues will be gone. We're going to do our flux thing. We're going to do our wrap it around trick. This is like 4 mil solder, so there's not much to it. Okay, then we're going to dump a bunch of heat into it until it melts. And surface tension should have it travel in that whole cleaned area for us. Does it look great? It doesn't look great, but it'll do just fine. We don't need that part anymore. And then I am probably in a good spot to shrink those and cover them. And shrink cover this one. This is our connector. We've got two for the bananas, which I'll grab another one in just a second. I've got ground and center, and it doesn't really matter which one's which. And this thing is now ready to install in the case. The thread, again, was really overkill. I don't think I would do that again on this design. It would have been fine to just have a slip joint. I did this because when I did the epoxy pour, I assumed the threads would keep the epoxy in. They did not, rather disappointingly. And now this thing isn't rotating around the last little bit. Oh boy, you guys are silly, aren't you? Come on. There's that. I have a couple of these kind of terminals to make my life slightly easier or slightly more difficult depending on your perspective. And I'm going to get them centered before I heat them up, and then I don't have to worry about getting the length wrong. And we'll come back and put on the rest of the hardware in just a second. I just need them to be approximately correct right now. That wire, I might have to cut that after once it's back out. Okay, what I've been working on is this. Probably should have shared that with you earlier. I'm going to solder those things in, but first I wanted them in the right location. You can never use too much flux, although you should clean it off afterwards, even if it's no clean. The difference between no clean and regular flux remains acidic, and it can slowly dissolve your joints, which is never a good thing. But you should always clean your boards afterwards anyways, because you never know what contaminants are on them from the manufacturing process or assembly process, or the Cheeto eating process. Funny thing in assembly houses, the contamination rates go up after breaks and after lunch. Okay, so those two are on and done. I'm going to take these off and put on the rest of the hardware. Let's see if we can heat that up a little bit more. Watch that flow. There we go. Next up, we've got to put that B and C in. The way that I did it in this other one, I don't know if we're going to be able to see it. I've got a little tab there. So we've got the center conductor done, and then I don't know if you can see it, but it's a little baby solder tab that I soldered to and then screwed to. That's how it's connected. But that's not the only way that I could potentially do it. I do know that I'm going to want to cover this, so I'm going to put on a little bit more heat shrink, and we'll get that stuff wrapped down and cleaned up. You're also supposed to use heat guns for this, not butane torches. Don't tell OSHA. Okay, so the first one that I'm going to terminate is this guy. Sorry to block your view there. So this guy is going to sit right there. I'm going to add a little bit of flux. I do have one last solder joint to make, but at that point you would take this, fill it with epoxy if you wanted to pot it, and there's some holes that, I mean, I would just glue the top on. You're never going to need to take this off anyway. And then there's some holes you can squeeze stuff through, but then that'll be it. That'll be your Balun. Now, I'm going to set this one aside because there's still one last bit of physics that I want to talk about. Remember that we said it needed to be balanced. Well, I need to prove to you that it is, and my oscilloscope needs to turn on for that. And what I'm going to do is check for balance. I do not need tools for that, but I do need a couple resistors. The antenna that we're making has characteristic impedance of, if I remember correctly, about 100, 130 ohms. Don't quote me on that because I'm doing that from memory. And the output of your radio, about 50 ohms. So what happens whenever you have an impedance change is the energy hits that interface and then it gets reflected back, and you never want that. So we typically make tuners that will try to match the impedances by storing the energy reactively. What I'm making right now is a resistor divider out of two 100 ohm resistors. So these resistors are going to be center tapped and tied together electrically at what we're going to call a ground point. And let's see if we can show this to you. Ooh, I don't think I need to be on screen for this. There we go. So I've just got a couple of resistors that are tied into this banana plug. Each one of these is 100 ohms. I have them wrapped around this center pin, and we're going to attach an oscilloscope ground here, a probe here on the left, and a probe here on the right. And what we're going to look for is, do we indeed have a balanced Balun? And then I need my scope probes. So this is probe 1, this is probe 2. That's our experimental setup. And what we're going to look for in just a second, I'm going to put the oscilloscope screen on, but what we're going to look for is, do we get a balanced signal at our frequencies of interest? For that, I do need a signal generator. I'm going to set up my SDR kits VNA to do that for me. So I'm just turning that on now. I need a 50 ohm feed line to go from the VNA output to the Balun input. So the VNA's providing single-ended, output. The Balun's doing its thing, and what we're going to be looking for is, do we indeed get balanced output here? the input, the single-ended input, up to my VNA and use my VNA as a frequency generator. And I'm going to set that to about 5 kilohertz. As soon as it loads, I'll share that with you. And I've got two plots. One, which you're probably used to seeing, which is a voltage versus time, but I also put up an XY plot. And I am just now hooking up scope probes. The scope probes are floating in space. They're not hooked up to anything. And in fact, I've got them grounded to one another. What you should see right now is nothing. There should be nothing on these probes. You can see that there's some common mode signal. As one goes up positive, the other goes positive. One goes negative, the other goes negative. Yeah, nothing I can do. There's going to be noise on this measurement. And what we're seeing is what we would expect to see. There is an equal and opposite output. So I'm sending 5 megahertz in, and we're seeing that on the output. I'm getting a roughly equal and opposite output. And that's exactly what you want. We're sending one signal in, we're getting two signals out that are 180 degrees out of phase. Ideally, what you would see on the XY plot is a straight line. I don't like that it's opened up, but I don't know if opening is because of a hysteresis in the Balun or if it's because of that offset that we saw, that common mode offset. And I'm pretty sure it's the common mode offset, because if I show you this plot without it, it looks a whole lot better. So when I have all of this crap off, I'm going to get out of the way, what we're seeing is a lot straighter line. There is still a little bit of jitter in here, but I have a lot of stuff on, but that's looking a whole lot better. Now, what you want to do then is pick different frequencies and see what happens. Now, I am at, 1 megahertz. I'm going to go back to my scope view here, and I want that to be a little bit more visible. So I am down to, I think, 1 megahertz or so, and you can see that that's really opened up. There's definitely a hysteresis there, and that has nothing to do with noise in the joint, but it has everything to do with the fact that I no longer really have a balanced output. The core is struggling to keep up. So keep an eye on that. I'm going to go back over here, and I'm going to go up to, say, 10, and then we're going to go back to our scope. I guess I can spread that out a little for you guys. We're seeing still a pretty decent, it'd be great if it wasn't open at all, but I don't know that that's noise or if that's not. But what we're seeing is as one goes very high, the other goes low. That's what gives you this negative slope. And that's exactly what you want. You want on your balanced output that you're getting 180 degrees out of phase output. And that's pretty much what we see. There's opening, there's jitter. Not ideal, but I'm in a noisy environment. So that's what we're seeing. We're going to keep pushing that number until this thing breaks down again. And this is how we can kind of get a general idea of over what frequency range this Balun's going to work. I'm currently at 25. We're looking pretty good. We're still seeing at 25 megahertz, we're seeing an equal and opposite balanced output. That's what we would hope to see. Let's keep pushing it and see what happens. Okay, I am pushing 50. This is probably a little bit past the end of what this thing should be doing. You can see that the amplitude has really fallen. I don't know if that's my function generator losing the ability to maintain the amplitude, but we've also seen our circle opening up. We could probably still operate at this, but this is probably the end of where I would want this thing to go. So at 50, are we working? Yeah. We're doing a whole lot better at the lower frequencies, and I would even say it's passable at the lower frequencies. But when we get down to 1, and then we're going to go a little bit lower, this core starts to saturate. 0 megahertz. That's too much lower. But let's go down to like 0.9, and we can really start seeing this thing open up. I don't know why it has to be. Okay, 9.5. We'll go there. And I'm going to back out again. And you can really see how we are definitely out of balance. So we're not really acting like a Balun anymore. For a Balun, you want equal and opposite amplitudes, 180 degrees out of phase, and we're just not seeing it at these low frequencies. So that's how you test your Balun to see if it's going to work in the frequency range that you want. Pretty cool, huh? I think it's pretty cool.